You are watching the lesson 4.2 video on exponential growth and decay. Notice how I have my Inspire calculator out, as you should as well. So if you don't have your calculator, it's important to stop the video now and go to a place where you can watch the video and use one of these calculators. Exercise 1, let's dive right in. It says that the number of people who have heard a rumor often grows exponentially. So we need to consider a rumor that starts with 3 people. We can see that right in the table. And every hour, the number of people who knows the rumor doubles. So we are multiplying by 2. Doubles means multiply by 2. Part A wants us to fill in the table. All right, we're multiplying by 2. So 3 times 2, 6. Times 2, 12. Times 2 again, 24, 48, 48 times 2, what is that, 96? Yes, 96 times another 2 is 192. So after 6 hours, 192 people have heard the rumor. We look at B, what operation is happening to the total number of people? Well, we are multiplying every single hour, or even more specifically, we are multiplying by 2. Next, it says to graph the situation and then label the y-intercept with its coordinates. What we're going to be doing over the next few lessons, or even the next few questions, is try to make that connection with our y-intercept once again. All right, graph. Let's graph these. After 0 hours, so here's our hours, our x. This is our x input and our output. If we input 0, we get out 3. And since each one of these is counting by 6s, 3 is going to fall right about here. And we'll label that 0, 3. So initially, 3 people knew the rumor. After 1 hour, 6 people knew the rumor. After 2 hours, 12 people, and so on and so forth. Let's continue to plot all of these input and outputs. Okay, so even though we only graphed from the beginning up until after 6 hours, you can see, make that a little bit bigger, it was a little off there, but you can see that this is growing at an exponential rate because we're not looking at a straight line. D says, why are we only graphing in the first quadrant? Well, let's think about it. Does it make sense to talk about negative hours or negative people? No, so negative people and hours just don't make sense. So they're not realistic. Okay, so E now says write a formula using before, now, next lingo and state the starting value. Well, since I am given 0, my y-intercept, let's use that. So the initial value, or the y-intercept here, is 3. How will we get to the next? Well, if we look at the now, what are we doing to the now? Well, isn't this our multiplier, the times 2 every single step of the way to get from one point to the next? So now times 2. And F wants us to use this pattern to write a formula for the number of people who knew the rumor. So we need to figure out how to get N of H if we know the number of hours. Well, where did this start? How many people knew this at the beginning? Well, 3 people knew it at the start, or maybe 3 people started the rumor. And every single hour we're multiplying by 2 over and over and over again. So how do we show times 2 over and over and over again? Well, that would be 2 to the variable power, because h would depend on the number of hours that went by. So we would multiply by 2 5 times if 5 hours went by. Now G is asking us a very important question. What significance do the two values we used in F, mainly 3 and 2, how do those relate back to the original problem? So what significance does 3 have? Well, 3 people started the rumor or knew the rumor initially. And then 2, what does the 2 indicate? Well, after every hour, so every hour, the number of people that know the rumor actually doubles. So I guess I should rewind a little bit and say, after I write a rule or any type of function rule like we did in part F, I typically will model it on my calculator. Let's create a new document, and I'm going to add a graph, and let's type in 3 times 2 to the h power. And if I hit enter, some weird slider message comes up. Why is this happening? Hopefully you're saying, oh, Mrs. Ruscio, you told us that our calculator only knows X and Y, and you are correct. So let's cancel this. And it looks like we need to change our H to the input value of X. Now we can see our function. Now we can see that exponential. And right away, you might notice that our window is much different. But what might be helpful to us right now is to hit Control-T to look at the table of values. Do we have 0, 3? Yes. 1, 6. 2, 12. Oh my goodness, oh my goodness. I could even use this table to make predictions about future questions or future hours, which is awesome. If I hide the table, again, we could go back through and we could change all of these if you wanted to. It looks like here we go up, almost up to 8. We don't really look at the negative numbers too much, so maybe -2 for each of these just to give us a little space. And it looks like we go all the way up to 204 and beyond. And as you can see here, we have a nicer model that helps us to see and model what is actually happening. Moving on to H, it says use this to predict. So we get to use this function to predict how many students will know the rumor after 40 hours. Oh, that's after almost 2 full days. Well, let's use it. N of, let's put in 40, and see what we get out. 3 times 2 to the 40th power. I'm just going to go ahead and add a calculator in here, and 3 times 2 to the 40th power. I'm not going to waste my time. Oh my goodness. Oh my goodness. That is a very large number. So let's write it down. 329 853 4 8 8 3 3 2 8. Well, this is a bit ridiculous. So there's a question that asks us down below, is this reasonable? And the answer is, of course not. This is probably more people than you would see even in the world. So this model might be only good up until a certain number of hours, which is something that happens when we use math to model real life situations. We will restrict the domain and say maybe this is only a good model up until 12 hours. After that, it becomes unrealistic. So take a minute, copy down what we just talked about. Moving on to exercise 2, we have Gene heading towards a lighthouse in a very peculiar, which means strange way. He starts 160 feet from the lighthouse. Okay, so starting, that means the initial value. On his first trip, he walks half the distance to the windmill. Okay, so half of 160 is 80, and so on and so forth. So take a minute, pause the video, fill in the table. This is what you should get. Well, what do we notice is happening to the distance? We're dividing by 2, aren't we? Below, it then says to write this as multiplication instead. This is extremely important to talk about. So how do we show dividing by 2 using multiplication? We can show this as multiplying by its opposite. So dividing by 2 is really dividing by 2 over 1. We just don't ever write it that way. So flip it, use its reciprocal. Next, let's graph. As you can see, I just plotted the points. I labeled the y-intercept just like they asked in part C. And I'm going to take a minute now to connect all of my points in a curve. And even though I keep getting smaller and smaller and smaller, or closer and closer and closer to the x-axis, I never actually touch the x-axis. That's interesting. All right, now D says write a before now next rule and state the starting value. Well, you know the drill. We're going to say that D of, let's say, 0, because that's our initial value. So here's our starting point is 160. And in order to get to the next, what are we doing to the now? Well, we could write it as now being divided by 2, but let's be consistent and keep that multiplier. So we're multiplying by a half every single time. E wants us to use the pattern we developed in D. We need to write a function giving the distance that's left, D of n, if you know the number of trips. All right, so how will we get the distance? How will we get D of n? Well, it looks like we started at a number, right? We started with 160, and every single time we multiplied by 1/2 over and over and over again, n times. So we're multiplying by 1/2 repeatedly. I want you right now to go ahead, let's add a new page on our calculator, and I'm going to graph this, and maybe I'm not too concerned about the graph at this point, but I definitely want to see the table of values. So I'm going to use parentheses. Let's throw those in there. And again, I'm not going to use n. I have to use x in my calculator, even though I'm writing n on my paper. If I hit enter, you can obviously see that my y-intercept is not showing on my window because, well, it only goes up to 6.67. And here we see it's 160. But for me, I just want to make sure that I came up with the right rule. I'm going to look at my table. Is 060 on there? Yes. 180, 240. Yes, 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 and so on and so forth. And like we talked about in the last problem, we could now use this to make predictions about the future. Part F, it asks what significance do the 2 values you used in E, so here we're talking about 160 and 1/2, what do they have, or what significance do they have relating back to the original problem? Take a minute, write something down. What does the 160 mean? What does the 1/2 mean? I'm hoping that you said that Jean is initially 160 feet away from the windmill. That word, that initially, is extremely important. So make sure you have that written down. And what does the 1/2 mean? Well, it means that every single trip he walks half the distance closer, or I should have actually probably put closer to the windmill. Now G says, when will Jean finally reach the windmill? So that would mean, when is he ever going to hit the x-axis? Well, if we go back to our calculator and scroll down in our table, our numbers keep getting smaller and smaller and smaller and smaller and smaller because we keep taking half. But the only way that we would ever be able to get down to 0 is if we were dividing 0 by 2 or multiplying it by 1/2, which will never happen. So is he ever going to reach the windmill? Never. He will get extremely close, but will never actually reach it.